Welcome to our lesson on motion graphs. We are going to talk about how our types of motion appear on displacement versus time graphs, velocity versus time graph, and acceleration versus time graphs. So our five main types of motion: standing still, moving at constant velocity, speeding up, slowing down, and turning. We have two of them have no acceleration at all, and three of them are the three types of acceleration: speeding up, slowing down, turning. Though today we're not going to worry about turning because all of our motion on our motion graphs really needs to be in a straight line, like forward and backward, right and left, or up and down. But it can only be along one of those lines at one time. Okay, so in our notes, let's just get some basic facts down really quick that are going to be important. We'll talk in detail about some of these facts, and we'll let some of them marinate for a while and visit them in deeper aspects later in the unit. Okay, so a displacement versus time graph. The slope of this displacement versus time graph, that is equal to velocity. What if I have a velocity versus time graph? The slope of that graph will be acceleration. And what's going on with these is if I have a displacement time graph, displacement is in meters, time is in seconds. If I take the slope, I'm taking meters over seconds, change in y over change in x. Oh, the slope is meters per second. Well, if I have a velocity graph where the y-axis is meters per second, and then the x-axis in seconds, meters per second. Oh, well, that change, that is acceleration. So the slope of a velocity graph is acceleration. But we also can do something else. We can take the area under the graph, the area between a line and the axis, and that is actually going to be equal to displacement. In other words, when I'm taking an amount of meters per second and I'm multiplying by seconds, well, that's going to get me to meters. And similarly, if I have an acceleration versus time graph and I take the area on that, the area under that graph is going to get the change in velocity. Now, this is a lot, and what we're basically talking about here is your first quarter, maybe your first semester of calculus. So pretty clearly, we could spend quite a bit of time in a calculus class going in depth on this. But for this class, the key things to know have to do with some simpler facts or a simpler piece of memorization. And to get from displacement to velocity or velocity to acceleration, you need to know that we are taking slope. And to go in reverse, from an acceleration time graph to velocity or velocity time graph to displacement, you need to know that we'll take the area. Now, we're not going to do a whole lot of calculations with these slopes and areas, but we are going to ask you to be able to identify quite a bit of these graphs and talk about what's going on with them in a qualitative fashion. So let's get into these. You should have this on your notes page, and you're going to want to follow this. You're going to want to be able to draw this in multiple colors, or maybe a pen and a pencil, or different colors of highlighters. But we're going to go through and have multiple graphs for each type of motion. So make sure you have your supplies and make sure you're ready. Okay, well, let's start with constant velocity, if we're moving at a constant velocity. And I want to start off with this because we've already done some work with this with your lab, taking a displacement time graph for the Blinky car, which was moving at a constant velocity. So we should have had a graph that went up at a pretty steady straight line. I don't have a way to do a straight edge with this, but a straight line increasing at a steady rate. All right, well, in order to fill in our graphs and to be able to talk about them, there are kind of three questions that are pretty important and should help you with this. First, is the slope on the graph that I'm looking at, is it positive? Is it negative? Or is it zero? Second, is my slope changing? And third, when we get into accelerated motions, we're going to want to say, if it is changing, how is the slope changing? So let's demonstrate what we're talking about here. We have our displacement time graph for the car. Is the slope of this graph positive, negative, or zero? It's positive. Is it constant or changing? Well, remember that if you have a straight line, if I take a slope at any point along that straight line, here or here or here or here, anywhere along there, it'd be the same slope all the way through. So if I were to go through and just plot those points where I'm taking the slopes, it's the same number all the way through. So that means my velocity is the same all the way through. And this is because, one, the slope of a displacement graph is velocity. Two, if I were to try and look at video of this and track the motion, we should be seeing the same change in meters per second all the way through. So I get a velocity graph that is a flat line, which seems a little weird to have a flat line graph for moving at a constant velocity, but that's what we're graphing here is velocity. It's the rate of change, and that change is staying steady. Okay, well, let's apply the same questions that I just talked about to our velocity graph, because it'll tell us about acceleration. Is the slope of this flat line graph positive, negative, or zero? The slope of any flat line graph is zero. And this one, the slope is zero all the way through. So my acceleration is zero all the way through for that. Can't quite draw it very effectively, but it should be zero there. Now, is it possible to have, is this the only possible graph that we could have for our constant velocity displacement? Well, what if we had the car going in the opposite direction? And I'm going to just draw a possible graph for a blinky car going in the opposite direction, coming back toward the start. Now, not only is this going in the opposite direction, but you may have noticed here that this slope, it's not as steep. So let's look at our questions again. Is this slope positive, negative, or zero? It's negative. Is the slope changing? No, it isn't. And when I compare it with the slope of my red line, I can see it's not as steep. So not only will it be negative, but it'll also be closer to zero because it's going to be a smaller speed. Maybe if this speed was positive 2, this one was only moving 1 meter per second in the negative direction. Now, you may have noticed that we skipped one type of motion here. It's actually the easiest type, and it's one that we would normally not even bother to graph, but it is, strictly speaking, a constant velocity. It could be a constant velocity of 0. Like if I put a rock down and it just sits there, like it started at this position and it just stays at this position all through time. Well, flat line on my displacement graph. Is the slope positive, negative, or 0? For my green graph here, it's 0. And the slope of a position graph, a displacement graph, is the velocity. So this is telling me that the velocity of the rock that's just sitting there is 0, which I would think so. Okay, so There's our first two types of motion shown there. Moving at a constant velocity, which can be in the positive or the negative direction, and for an object just sitting still. We have velocity graphs that show that. Constant positive, constant negative, or constant zero, the extremely boring one. Okay, so let's look at a more exciting type of motion, increasing speed. In other words, speeding up. So the displacement time graph for this motion, it's going to start out not changing very much if you're starting out slow. But as it speeds up, as it covers more and more ground with each second that passes, then my slope is going to get steeper and steeper. Okay, well, what's the velocity graph for that going to look like? We should see a changing velocity. And when I ask myself my slope questions over here, is the slope positive, negative, or zero? We have a bunch of positive slopes here. Is the slope changing? This one is changing. Any curved line is a changing slope. Well, then the question is, how is the slope changing? And my important piece of advice here is look for where you have the most shallow or even the flattest slope and where you have the steepest. Where you have a flat slope, this one starts off with a flat slope, that means my velocity is zero. And where I have a steep slope, that means, well, I have a steep positive slope, I have my highest positive velocity then. And all the slopes in between are changing from zero to this steep positive. So my velocities are changing from zero velocity, going up at a steady rate to my maximum positive here. Okay, now to simplify things, in this class we're always going to assume that velocities are changing in a straight line like this. What this means is that we only have constant accelerations instead of changing accelerations. That's not every type of motion we ever see. There are some speeding up motions where the rate of change itself is speeding up, but you're not going to see that all that often. And so this helps us understand most of what we see in the everyday life. All right. Well, remember I just said constant acceleration? Let's look at our acceleration graph and ask ourselves the slope questions. What kind of slope do I have here? Positive, negative, or zero? Positive. It's going uphill. Is it constant or changing? Straight line graph. That means I have a constant positive slope. So I have a constant positive on the graph that's right underneath it. Constant positive slope on velocity means constant positive, trying for a flat line graph here, on my acceleration. This isn't the only type of speeding up though. This was speeding up in the positive direction. So I have a increasing positive velocity. But I could also have speeding up in the negative direction. So this is a negative velocity, and we have to remember that negative is just a direction. We could be moving backwards, or that you could be moving downwards, and often we would say down is negative. So as my slope goes negative here, we have to understand that that means moving faster and faster in the negative direction. Slope starts off flat. Oh, well, is the slope positive, negative, or zero? It's negative. How is it changing? It's going from a flat, in other words, a zero spot, to a steeply negative. It's the opposite of what we saw on our previous one. And in fact, I'll try to match up my point in time here. So very negative velocity. And so we're seeing this as my slope gets more and more steep and negative, my velocity is getting more and more negative. Okay, what about the acceleration? Well, this slope is a negative and constant. So we have a constant negative slope on my velocity graph, so a constant negative acceleration. Again, this should be a flat line graph. Not perfect at drawing that. All right. Well, so we've done standing still, moving at constant velocity, speeding up, and we still can do slowing down. So if I'm moving in the positive direction, but slowing down, that means I'm going to start off moving a lot with a steep slope on my displacement graph and leveling off. So on a displacement graph, leveling off means slowing down. So slope positive, negative, or zero, generally positive. Constant or changing, changing. And remember our trick of look for where the slope is flat, because that will help me say, oh, on the graph below it, if my slope is flat on displacement, my velocity graph should be zero at that point. We started off steep. So I start off with that positive velocity, and it decreases as this thing levels off. So here's for positive velocity, decreasing speed. In other words, slowing down. We see it leveling off. We see the velocity going to zero. And that means I have a negative acceleration. So this tends to throw people a little bit because this positive velocity means you're moving forward, but you're slowing down. And that means I have an acceleration that is against it. If my velocity is positive, my acceleration has to, in order to slow down, my acceleration has to be opposed. It has to be in the opposite direction. So this takes a negative acceleration when I have a positive velocity to slow it down. The flip side of that is to have something that has a negative velocity and negative change in position, but leveling off. That leveling off motion is our clear sign that we're slowing down. So I started off with a steep negative velocity, and I ended with a flat slope, meaning I have a zero velocity there. So this graph tends to throw people off because they see the line going up. But what's that mean it's doing? It's getting close to zero here. We started off with this negative velocity in the negative direction, a large number, and it goes down, it decreases in size by moving towards zero. Well, what kind of acceleration graph is that going to be? Well, the slope here is positive and constant, so I have a positive acceleration. So again, that's pretty counterintuitive, but remember that in order to slow down, we need an acceleration that is opposed to our velocity. So if I had a negative velocity, my acceleration is going to be in the positive direction to oppose that. And that's what causes it to stop moving in the negative direction, and in fact, in this case, even come to a stop. Okay, I encourage you to practice this, practice this, practice this. This takes a lot of processing and work, but if you build your understanding in this, you will have a deep understanding of the way that things move and a really good start on calculus. Thanks for watching, and we'll see you in the classroom.